So, okay. Yeah, so my name is Lisa, and I'm an instructor in radiology at the Gordon Center at MGH. And I work with radiation detection and instrumentation, mainly for nuclear imaging applications. And I'm going to give 2 lectures this week, as Moses said, about radiation detectors and counting statistics. So today, I plan to go through the basic concepts that can be applied to any radiation detection system, not just medical imaging systems. And in the next lecture, I will go into more details on detectors and detector requirements and detector characteristics with the application of medical imaging in particular. And I also wanted to say that if there's anything from today's lecture that you would like me to talk more about next on Thursday, or that you felt was unclear or need clarification, feel free to let me know and I can incorporate that into Thursday's lecture. So you can either shoot me an email or just let me know after the lecture today. Okay. So this is just a very short outline, what we're going to cover today. I will start by briefly talking about interaction of radiation with matter, because this is essential in order to understand how radiation detectors work. I think Moses touched on this in the last lecture as well, so it might be some repetition, but I think it's good to go over it in conjunction with the radiation detector lecture as well. And then I will talk about the main topic of today, which is radiation detectors. I will talk about how a basic radiation detector works and also describe the working principle of different types of radiation detectors. And finally, I will also cover some counting statistics. So, and if you have any questions during the lecture, you can interrupt as you go or save the question for last, whatever you feel is better. Okay. So here are just some useful references in case you want to read more in more detail about this topic. I've been using mainly the second 2 references when I prepare this talk on this lecture. So first, as an introduction, so for a radiation detector to work, a radiation detector you want to use to measure radiation. So for it to work, you need the radiation that you want to detect, you need it to interact in your detector material and leave some kind of trace in the material. And by leaving a trace, we mean depositing some or all of its energy within the detector. And from this energy deposit, we can draw conclusions about the radiation that it came into the detector, which is the whole purpose of a radiation detector. So the idea is to have your radiation interact in your detector, get a signal from that interaction, and that would give us information about the radiation. So we generally divide ionizing radiation into 2 types, charged radiation and uncharged radiation. And the reason is because the interaction mechanisms, the things that happen inside the detector are very different depending on which type of radiation you're dealing with. For charged radiation, such as positrons, beta particles, alpha particles, you will have interaction between the nuclei and the electrons in the material through the Coulomb force. But for uncharged radiation, you will not have that type of interactions. You will have different mechanisms. And uncharged radiation is, you put the neutrons and photons in this group, and photons is what we will focus on in this lecture. So photons are neutral particles, so they are a kind of uncharged radiation. And this is the type of radiation that we want to detect in nuclear imaging applications. So in PET, we want to measure the 511 keV annihilation photons that are generated when the positron emitted in the decay of our tracer annihilates and emits 2 back-to-back 511 keV gamma rays. And in SPECT, we want to measure the single gammas that are emitted directly from the radio tracer and the energy of these are typically lower compared to the energies that we have in PET. So in the next slides, I will describe the interaction mechanisms that we have for photons, which are the following. We have photoelectric absorption, Compton scattering, pair production, and Rayleigh scattering. And different mechanisms are dominant for different photon energies and different types of detector materials. So first we have photoelectric absorption. So this is an atomic absorption process. So the atom, you have our incident photon, and the atom absorbs the full energy of this incoming photon. And as a result, a photoelectron will be ejected from the atom. And the kinetic energy of this ejected photoelectron will correspond to the difference between the energy of this incoming photon and the binding energy of the ejected photoelectron. So the energy of this photoelectron will carry some information about the energy of the incident photon. So this atom is quickly left ionized because it loses one electron, and it has a vacancy in one of its bound shells. And this vacancy will then be quickly filled by capture of a free electron or a rearrangement of the orbital electrons. So therefore you will typically have also one or several characteristic X-rays that will be emitted. And these X-rays are typically reabsorbed very close to the interaction point because they have such low energy, but they may escape the detector, which can impact the response because you will lose some of the gamma ray energy. And also we can see that if we have a higher energy of our incoming photon, the probability of photoelectric absorption will go down. So the second mechanism is Compton scattering, and this is a collision between the incident photon and an outer shell orbital electron, like we see here. And the result is a scattered photon with lower energy compared to the incident one, and also an ejected Compton or recoil electron. And the energy of this scattered photon can be determined as a function of the scattering angle, as you see here. So this equation relates the energy of the scattered photon with the energy of the incoming photon and the scattering angle. So this you can deduce simply by using laws of conservation of energy and momentum. So the probability of Compton scattering will depend on the number of electrons that you have in the material, and it will increase with atomic number and density of the detected material that you have. So this slide shows the probability distribution of different scattering angles for different photon energies. So we have the scattering angle here and the probability of that scattering angle to occur. And these are different energies of the incoming, of the incident photon. So we have 10 keV, 100, 500, 1 MeV, 5 MeV. So we see that when we have low photon energies, all scattering angles are more or less probable, equal probability. But when we go to higher energies, small scattering angles are significantly more, have higher probability compared to large scattering angles. And then the third mechanism we have is pair production. And for pair production to occur, the energy of the photon must be higher than 2 times 511 keV or 0.5 MeV, this is the rest mass energy of an electron. So in this interaction, the photon energy is converted into a positron-electron pair. And the excess energy of the photon, like above this number, will be shared between the positron and the electron as kinetic energy. And the positron will slow down quickly and eventually annihilate with the generation of 2 511 keV back-to-back gammas. So you see that the positron will will annihilate, and you will get 2 annihilation photons. So this mechanism is not it's not significant in most nuclear medicine applications because of the high energy that you need. We remember that in PET, when we have 5 LA in keV, which is way too little for PET production to occur. And the fourth interaction mechanism is Rayleigh scattering. And here the photon is scattered on the atom, and very little energy is absorbed by them due to the large mass of the atom compared to the large mass of the atom. And the photon is deflected, and it loses very little energy. So this process is important only at very low photon energies, way below 50 keV. So this slide just summarizes these interactions. So the main interactions that we have are photoelectric effect, Compton scattering, and pair production. And this shows when each of these interaction mechanisms will dominate. So we have as a function of the energy of the incident photon and the atomic number of the absorber or the detector material in our case. And for in our case in medical imaging, we typically we're working in this region. So we will have photoelectric effect and Compton scattering mainly. So then we can move to charged particles. And here, as I mentioned, the type of interactions are different. Charged particles include electrons, positrons, and alpha particles, and we will talk mainly about electrons. So there is a difference between the path that a photon will take when moving through a material and that the electron will take. So for photons, we will have these interactions that I just described, and it would happen in discrete locations. So the photon will travel, something will happen, maybe Compton scattering here, and the photon will move untouched until the next thing happens. So the path would be straight in this sense. For electrons, however, given that it will continuously interact with through the Coulomb force with the atoms and the electrons, or the nuclei and the electrons in the material, we will have a gradual energy loss. So it will gradually lose energy by energy transfer to nearby atoms. So the path would be continuous in that sense. So the range, while a photon can, depending on its energy and the material that it travels through, it can travel very long distances without anything happening. But for electrons, it will continuously lose energy. And the range of an electron is also smaller compared to the range of a gamma photon. And the range is determined by the density of the material as well as the energy of the electron. So for this type of radiation, we have 3 interaction mechanisms. We have ionization, excitation, and bremsstrahlung. So ionization happens due to interaction between the charged particle and an orbital electron. So the charged particle will transfer energy to the electron. And if this transferred energy is larger than the ionization potential, the electron may escape. And you will have a secondary electron. And excitation is similar, but the transfer energy is not enough to completely free the orbital electron, but it's left in an excited state. And this excitation energy will be dissipated by molecular vibrations or atomic emissions of photons in the UV, visible or infrared range. And the final mechanism is bremsstrahlung, and this happens when the charged particle interacts with the nucleus. So here it's the nucleus instead of the orbital electrons that the other 2 mechanisms were. So it interacts with the nucleus, because in the vicinity of the nucleus we will have a very strong electric field, which will deflect the charged particle that comes near here. So it will change, it will lose energy, and it will change its direction. And this lost energy will appear in the form of electromagnetic radiation. So in this slide, I just wanted to summarize what we talked about in the previous. So we assume that we have a detector and we want to measure gamma radiation. So the incoming gamma can interact in different ways in the detector. We have photoelectric effect, Compton scatter, or pair production. And in the case of photoelectric effect, we get a photoelectron as a secondary radiation in the interaction. And for Compton scattered, we will get a scattered photon of lower energy, which can then continue to interact in the detector through these mechanisms. And we also get a secondary electron in this case. And for pair production, we will get an electron and a positron, and also secondary gamma rays. So we see that with all of these photon interactions, we will also get secondary electrons generated within the detector that will go on and interact through ionization, excitation, and Bremsstrahlung. So even if we want to detect photons, both photon and electron interactions are important. And I also wanted to say here that the signal that we get from the detector, ideally we want the signal to be proportional to the energy of the incoming gamma ray, so the energy that came into the detector. And the prerequisite for this to happen is that all of the energy of this incoming gamma ray is deposited in the detector material. So even if the gamma interacts in the detector and some of the, so if the gamma interacts in the detector and some of the secondary radiation escapes from the detector, we will lose information and we can't accurately determine the energy of the incoming gamma. For example, what happens here? Here we see that one of the annihilation photons escapes from the detector. So we will have a lower energy that is measured compared to the energy that was incident on the detector. So the next concept I wanted to mention is photon attenuation. So this equation, which is pretty bad quality, I see here now, but this tells us about the amount of material that we need to stop a certain fraction of incoming photon radiation. So if we have an incident photon beam with a certain intensity that hits a material, as shown here, part of this beam, part of the photons will interact in this material and be lost essentially, and part of it will just travel through without anything happening. And the amount that will be that will interact here, or the amount of the fraction of the beam that will interact in the material will depend on the thickness of the material, the properties of the material, and on the energy of the incoming photons. This equation relates the intensity that we would measure. If we would put the detector on the other side of the material to measure how much radiation is coming through, this equation relates this intensity that we will measure here to the intensity that was incident on the material. And it depends, as you see, on the thickness of the material and on mu, which is the attenuation coefficient. And this is a energy dependent coefficient, which is also specific to each material. So the equation can be used to calculate either the amount of shielding material that you will need for a certain application to protect people or things from radiation, or to determine how much detector material you would need to achieve a certain detection efficiency. So this is a very useful equation. Okay, so now let's move to the actual radiation detectors. So we know now that radiation will interact in the medium that it goes through, and this will happen regardless of what type of medium we have. But the rates and characteristics of the interactions will differ depending on the material. And for a radiation detector to be useful, we wanted to be able to measure these interactions, so this energy deposit in the detector. So this means that we need to convert this into a signal that we can analyze. So, and as we've seen in the previous slide, the radiation interactions can cause generation of charge in the detector volume. So what we want to do is to collect or measure this charge to form an electric signal that we can analyze. So depending on the application, radiation detectors are used to determine where radiation comes from, how much radiation there is, and what energy and type this radiation has. So this is a schematic of a detector. So we have radiation hitting the detector material and interacting in here, and we would get as an electric signal as a result of this. And this signal can then be amplified and converted to a digital signal and then be stored and analyzed. So today I will talk mainly about the first part of this figure, which is the actual detector, what happens here. So a detector system can be operated either in pulse mode or in current mode, depending on the type of detector and the application that you have. So in pulse mode, you will get an individual pulse as a response to each incoming radiation quanta, or each gamma photon in this case. So there are different types of detection systems that uses detectors operated in pulse mode. You have counters that simply measure the number of interactions in the detector without providing any information about the energy of the incoming radiation. And then you have spectrometers that measure both the number of interactions and also the energy of individual radiation quanta, or photons in this case. So the size of the pulse in these systems is ideally proportional to the energy that was deposited in the detector by one radiation quantum. So nuclear medicine systems like PET and SPECT are operated in pulse mode, because here we want to know both the energy, the intensity of the radiation, and also its spatial origin. And the second mode the detector can be operated in is current mode, that will measure a photon flux instead of individual photons. So in this case, many interaction events are averaged, and the average current generated in the detector is proportional to the event rate and the average charge produced per event. So detectors in current mode are used in dosimeters and also in conventional CT systems. So now I will talk about three different types of detectors that are used for photon detection. So we have gas field detectors, semiconductor detectors, and scintillators. So these first two detectors are directly converting the radiation energy to charge. So this means that we are directly measuring the ionization and excitation that we produce in the detector material. But in scintillators, we have indirect conversion. So this means that the ionization and excitation inside the detector material causes emission of visible light. And then this light can be collected and converted to an electrical signal by a photodetector that you couple to the scintillator material. So this is a two-step process, meaning indirect conversion. So you go from ionizing radiation to visible light to an electrical signal. And scintillators are the most commonly used detectors in nuclear imaging. So if we start with gas field detectors, so this is a schematic picture of how this works. So we have the incident radiation here entering the detector material, and it causes ionization in a gas that can be either air or other gas. And if we apply a voltage across this gas volume, the free electrons will migrate to the anode, and the positive ions will migrate to the cathode. So this results in a current that we can measure over here. So depending on the size of the voltage that we applied here, gas-filled detectors will behave in different ways. And it's common to talk about 3 different types: ionization chambers, proportional counters, and Geiger-Müller counters. So ionization chambers are air-based chambers that are operated at low voltage. So here you see a plot of the amplitude of the output pulse here on the y-axis as a function of the applied voltage. So the first part here corresponds to what you call the recombination region. So here the voltage is too low to collect all the charge that we generate in the detector. So part of the ions and the electrons will recombine before they reach the anode and the cathode. And if we increase the voltage in this region, the recombination will decrease and we will get a larger signal. So the signal will be increased with increased voltage. But when we reach what we call the saturation voltage, then all the charge is collected. So no recombination occurs anymore. And if we increase the voltage further beyond this point, the amplitude of the output pulse will not increase because there are no more charge to be collected. So you want to operate the ionization chamber above this saturation voltage. But the signal from an ionization chamber is very low, so their use is kind of limited. A few applications are survey meters that are used to monitor radiation levels for radiation protection purposes. And then there are also dose calibrators that are used to measure activity levels in syringes and vials that contain radio tracers. And also pocket dosimeters may use ionization chambers, but they are very inefficient for X-rays and gamma rays. So if you continue to, before we were in this region for the ionization chamber, and if we continue to increase the voltage, we have the same plot, the continuation of that same plot here. So we have amplitude of output pulse and the applied voltage. So if we continue to increase the voltage further, we will enter the proportional counter region. So this is above the threshold for gas multiplications, meaning that when we get above this voltage, the electrons will be accelerated with such high velocity that it causes them to cause more ionization when they collide with gas atoms on their way to the anode. So this is called the Townsend avalanche, or gas amplification of charge. So if we increase the voltage, the signal is increased further because the probability of causing further ionization will increase with increased applied voltage and energy of the accelerated electrons. So these type of detectors, they can have an amplification as high as a factor of 10 to the power of 6. So the higher signal that we get a higher amplitude pulse that we get from the ionization chamber. It's higher compared to what we get from the, So the signal in the proportional counter is higher than the ionization chamber. And the signal is proportional to the amount of energy in the detector. So this can be used in pulse mode. It still has low sensitivity to higher energy radiation like X-rays and gammas, because we're still dealing with gas. We have low density and low effectiveness. But it can be used to detect alpha and beta particles that have shorter range compared to photons. And the third type is the Geiger-Müller counter. And here we have an even higher voltage compared to the other two cases. So you have the ionization chamber region, the proportional counter region, and then we enter the Geiger-Müller region. So at these high voltages, the signal is no longer proportional to the energy deposited in the detector. But the output is large, but nearly independent of the energy of the incoming radiation. So this can be used to count individual events, but you can't get any energy. It doesn't provide any energy information. So second type is semiconductor detectors, and they have a similar working principle as the gas field detectors. So they respond to radiation by electron hole pair production. And then you apply a bias voltage across your detector volume to make your charge drift to an anode and the cathode to generate a measurable current. So the difference between semiconductors and the gas field detectors are that semiconductors are solid, so much higher density compared to gas field detectors. So they can be used to detect also gammas and X-rays, because you will have higher interaction probability for these radiation types. So we can see in the table here, we have the density and the effective C for some common semiconductor materials. We have silicon, germanium, and cadmium telluride. Compared to air. So we see that there is a huge difference when we compare the density, especially in the density, when we compare the air and the semiconductor materials, but there is also a big difference in the effective C when we compare air to these materials. So this means that we will have much higher interaction probabilities for gamma rays in semiconductors compared to air. And we also see the work function in this table. So this corresponds to the energy that's needed to create one electron hole pair in each of these materials. So we see that this energy is much lower for the solids compared to air. So this means that for a given radiation energy, we will produce a lot more electron hole pairs in the semiconductors compared to in air, which will result in a higher signal and also in a larger number of charge carriers, which is important because this will be the limiting factor which determines the accuracy that we can determine properties of the incoming radiation. And the signal that we will get is proportional to the deposited energy. So these type of detectors are typically operated in pulse mode. But one problem with semiconductor detectors is that they have thermally induced noise. So this means that electron hole pairs can be created just by thermal vibration without any radiation interacting in the detector, which will increase the baseline of your output signal. So because of this, a lot of these materials need to be cooled to work properly, because the colder they get, we can reduce the probability of the thermal noise. So therefore, they need to be cooled, which makes them a little bit more difficult to handle, because there is an extra step of an extra mechanism that's needed. And there can also be, if you have impure materials, like if you have impurities in the material, they can act as traps for the electrons and holes, which will lead to signal loss. So to limit this, you want to have high purity material, which is expensive to make, and it also limits the size of the pure crystals that you can achieve. And many semiconductor detectors also have donor impurities that compensates for the trap, but this is also expensive and time consuming, and you're limited in the thickness of the material that you can achieve. So because of these thickness limitations and the price of semiconductors, the use of them is somewhat limited, and they're used in some SPECT systems, because in SPECT we have lower energies compared to PET, but they're not great for high energy gammas if you want to have high efficiency at a reasonable price. So then we can go to the third detector type, which is scintillators, that are very common in medical imaging applications. So scintillators are based on the mechanism of luminescence. So luminescence is the emission of light after absorption of energy. And this can occur in many different types of systems as listed here. We have photoluminescence, which is emission of light as a response to light. We have thermoluminescence, sonoluminescence, electroluminescence, etc., etc. So it's quite a common mechanism. So scintillators, they emit photons or visible light. So these are visible photons following the excitations of atoms and molecules in the material by radiation. And this radiation can be gammas or particle radiation, like betas and alpha particles. So there are different, and this light that is emitted can be of different, there are different types of emission based on the time scale of this emission of the light. So we'll have fluorescence, which is an emission that occurs very shortly after the excitation, approximately 10 nanoseconds. And then we have phosphorescence, which is similar to fluorescence, but the re-emission of the light is not immediate. So there is a time delay between the excitation and the emission of the visible light. So we want as high fraction as possible of the emitted light to be of fluorescence type, because that will give us a shorter signal and allow for better timing performance of our system. So this is a schematic picture of different components of a scintillator detector, just to make it clear. So we have the scintillator material, and we have a gamma coming into the material. And what's going to happen is that we will get emission of optical photons that we see here. And these will travel through the detector material and be scattered and reflected at surfaces, and then finally collected by a photodetector that we couple to the scintillator. And typically the scintillator is wrapped in a reflector material to increase the amount of light that we will collect here. So then the signal from the photodetector is the electrical signal that we will use for analysis. And there are many different types of scintillators. They can be fabricated in different shapes and sizes, which is one of their advantages. And the emission spectrum, meaning the energies of the optical photons, they vary between materials. As you can see here, there are different colors in these different crystals or different scintillators. And as I already said, they need to be coupled to a photodetector to collect this light signal. So there are many materials that will show luminescence, but for it to be a useful scintillation detector, it has to fulfill some requirements, which is high light yield, meaning that we want to have high efficiency in the conversion between the excitation energy into fluorescence. And we also want it to be transparent to its own scintillation light, to its own fluorescence light, because if not, the light that is emitted will be absorbed within the material itself, and then we can't measure it, it won't contribute to the signal. And we also need the emission spectrum, meaning the energies of the visible light or the optical photons that are generated. We need them to match the spectral sensitivity of the photodetector, because we need this conversion to be as efficient as possible. So all of these three factors are important, because more light will give us a better signal. We want to collect as much of the light as possible. And we also want a short decay constant, because we want the signal to be relatively fast. And this is especially important when we have applications where timing is important, and also when we have high count rates. Because if we have very high count rates and very long signal, we will have a pileup of the pulses from the detector, which will reduce the performance. So there are different types of scintillator materials. And one subgroup is inorganic scintillators, which is the type that's usually used in nuclear imaging. And there are also other types like scintillating gases or plastics that are doped with scintillating molecules. But inorganic scintillator crystals, which we will talk about mainly here, they feature crystals that feature band structure, like we see here. So the band gap between the valence band and the conduction band is about 5 to 10 electron volts. So what happens is that the absorbed energy excites electrons from the valence band conduction band. And then recombination will eventually occur. And when this happens, this will cause the emission of a photon. And this transition probability is increased by using these activator centers, which can be dopants that you introduce into your crystal. And these activators or dopants are tailored so that the detector will emit light in the visible range with a good wavelength. So this is a really big area of research to find crystal host and dopant combinations that will give you a crystal with good properties for radiation detection purposes. Yeah. So this is an example of a pulse shape from a scintillator. So they typically show a simple exponential, many of them show a simple exponential decay. And if you have several signal components, you can have different components with different decay times, because different transitions for the recombination can have different time characteristics. And if you have different components, your total signal will be a combination of the individual components. Like in this case, we have a faster component and then a slower component. And this will be our total signal. So the rise of the signal is typically very fast. And then the decay can be described by a sum of exponentials depending on what type of material you have. So these exponentials are characterized by one or several decay constants. So I already mentioned that light output is very important because it will determine the size of the signal that you ultimately get from your system. So this is in semiconductor detectors and gas field detectors, the limiting factor in the accuracy of your system was the number of charge carriers or electron hole pairs. In a scintillator, the limiting factor is the amount of optical photons that you get to interact with your photodetector. So there's only a few % of the deposited energy in the detector that's transferred to light. And the mean energy that you require to create one optical photon will differ between different materials, as you see here. These are 3 different types of scintillators. So you can see that they will have different light yields. This detector, the sodium iodide, will have a much higher signal or larger number of optical photons compared to BGO if the same energy is deposited within these materials. So these anthracene and sodium iodide are often used as reference material. So the light yield is given in percentage of the yield of these 2 scintillators, because these are very old standard scintillator materials. So in addition to a loss in, like, not a perfect efficiency in the conversion of energy to optical photons, you will also lose photons in the scintillator itself due to reabsorption, or you will lose it at surface surfaces or in the light guides that you use to couple your detector to your scintillator to your photodetector. And then the efficiency of the quantum efficiency of the photodetectors. The quantum efficiency is defined as the fraction of incoming optical photons that are transformed into photoelectrons. This is typically only about 30%. It differs depending on the type of photodetector that you use and also on the energy of the optical photons. But this number is more to appreciate how much light is lost in the process. So this slide just shows a different emission spectra of different crystals. So you see that for all of them, they have, so this is sodium iodide, for example. So you will have a distribution of energies of your optical photons that are generated. That's, in this case, it peaks around 400 something nanometers. And the emission spectra can be very different depending on the type of material that you have. So this is just a list of different common scintillator materials and different scintillator properties. So there's often, like when we look at these materials, there's often a trade-off between different properties. So you need to decide which property is most important for the application that you're working with. So we already talked about light yield, that this is important. And we also have the decay constant, meaning that the timing properties of your scintillator. If you have an application where timing is important, you want this decay constant to be as low as possible. And this is the emission wavelength. This is the peak of those distributions that we looked at in the previous slide. So you can see also here that they differ quite a bit between different materials. And then we have the refractive index of the material, which is important because when we couple the scintillator to the photodetector, we want to be able to match the refractive index of the crystal with the refractive index of the photodetector so that we don't lose a lot of light in this interface. And then we have density of different materials, which will determine the interaction probability. So this is related to, this shows the thickness that's required to stop 50% and 88% of 500 keV gamma rays. So we see that they also differ quite a bit between different material. And this also shows that many scintillator crystals are hygroscopic, meaning that they don't like humidity. So some of them need to be like enclosed in a airtight enclosure and not to deteriorate over time, which is an added complication of some of these materials. So we can see here we have, to give some examples, we have sodium iodide and cesium iodide. These two materials are used for SPECT, but the stopping power, you see here, the density is relatively low, which means that they're not very good for PET because there we have higher gamma energies. And they are also relatively slow, which means that they're not good for timing application. Like for PET, we often want to use time of flight information, and for that, timing is important. So that's also a limiting factor for these materials in PET. And then we have another example is lanthanum bromide, which it has high light yield and it's very fast, but it has relatively low density. So here we would need a very thick detector for it to be useful in PET also. So the types of detectors that typically used in PET is BGO and LYSO. LYSO is a newer material. BGO has been around for much longer. You can also see that the properties of LYSO is better compared to BGO. The light yield is higher, they're faster. This refractive index is easier to work with, because typically you want to couple a photodetector with, you want to couple it to a photodetector with a refractive index of around 1.5, which means that the efficiency that you can extract the light is going to be higher for LYSO. And it has comparable density. So the advantage of BGO compared to LYSO would be price, because it's a cheaper material compared to LYSO. So this slide basically summarizes what we talked about in the previous slide, that we have different choice of detector material depending on the application. And there are different characteristics that are important for different applications. So we have the intrinsic spatial resolution of your detector, which depends on the photodetector, the detector size and the photodetector size. So this, when choosing your detector material, can be, you would need to consider how easy it's going to be to fabricate small detector pixels, for example, of a given material. And second is detection efficiency, and we want high density and high effective C to stop as much radiation as possible. And this property is more important for applications where we have higher energy radiation that we want to measure. And energy resolution is another important factor, which is determined by the light output of your detector that we talked about. And then count rate, we want fast decay time to avoid pulse pileup if we have high count rate applications. And finally, an important factor is cost, because the total cost of any medical or nuclear imaging system, a very large fraction of that price tag comes from the detector material used. So this really is something that you need to consider when developing a new system, because it's going to impact the cost of your detector material, and the amount of detector material needed is going to affect the cost of your system, and then ultimately the usability of your system. Yeah. So the second component in a photodetector or in a scintillator detector is the photodetector, which is used to convert the light to an electrical signal. So one important requirement is that you want high sensitivity, which we already talked about, is expressed as the quantum efficiency. So this is the fraction of the number of photoelectrons divided by the number of photons that hits the photodetector. And there are different types of photodetectors that are used in nuclear imaging. And we have photomultiplier tubes, PMTs, and silicon photomultipliers, SIPMs. These are the two main types that are used. So a photomultiplier tube, this is the traditional older photodetector that's been used for a really long time. So here you have photo emission from a photocathode. So you will have your light photon reaching your photocathode here, which will result in the emission of a photoelectron. And then you apply a high voltage across this tube. So you will accelerate your photoelectron and reach a dynode where it will be having higher energy compared to here. So it will interact here, and more it will multiply in each of these steps. So you can reach a very high gain depending on the number of dinodes that you have, and depending on the voltage that you apply. As we say, we can have a very high dynode gain, but this type of detector is very sensitive. You can appreciate, because we have acceleration in these different stages. It's very sensitive to magnetic fields. So you can't use it in, if you want to develop an MR compatible, magnetic resonance imaging compatible system, these detectors cannot be used because they will not function properly. And for a photomultiplier tube, the photocathode material is very important. So this quite messy slide shows the quantum efficiency as a function of wavelength for some different photocathode materials. So the take-home message here is mainly that different photocathode materials are sensitive to different wavelengths. So these spectra that we see here, we see that they will all peak like around a certain wavelength. So for an efficient detector, we want to match this spectrum with the emission spectrum that we saw for the scintillator itself. And this shows different dynode configurations. So these are the accelerating stages. So they can look in very different ways, like the actual geometry of things, but it's all about accelerating electrons and focusing them onto the next stage or the next dynode. So the second type of photodetectors is silicon photomultipliers. So this is a little bit different. So here we have an array of very small avalanche photodiode cells on a silicon chip. So each cell is around 10 micrometers, so it's very small. And then you have a bias voltage on the chip that's large enough so that you will have an avalanche of charge generated from a single photon. So this avalanche is self-sustained and it needs to be quenched by an external circuit. And because these cells are small enough, the probability of a photon, of more than one photon interacting in the same or hitting the same cell is pretty small. So this means that the amount of, or the number of fired cells in an array is proportional to the number of incoming optical photons. So this means that if this is true, the number of fired cells will correspond to the energy of your incoming radiation if the number of optical photons corresponds to your incoming radiation energy. So there needs to be linearity in all of these stages. So this is what I just said, that the number of cells needs to be large enough so that the probability of a photon hitting an individual cell is small. And the advantage of this type of photodetector is that they are insensitive to magnetic fields, as opposed to photomultiplier tubes, which makes them very interesting in nuclear medicine for MR compatibility. So now we'll move to the last part of this lecture, which is counting statistics, which is a very important concept in radiation detection. So in any measurement, you will have an error or an uncertainty. So this error can be of different types. It can be a blunder, something that was done wrong with the setup of your measurement, or it can be a systematic error, so that your result will differ consistently from the correct result by some fixed amount. So if you repeat your same measurement several times, you will have the same result, but that result will be wrong. So the systematic errors will affect the accuracy of your measurement. And then you have random errors. And these are can be related either to equipment limitations of your measurement system, or it can be random variations of your measured quantity, which in the case in a radiation counting system, you will have inevitable random variations in the measured quantity because radioactive decay is itself a stochastic process. So random errors will affect the precision of your measurement. So given that radioactive decay is a random process, so if we imagine that we want to measure the activity of a long-lived radioactive source using a properly operating measurement system, this can be done if we measure the number of counts that we get, so n is the number of counts, during a given time. And from that, we can calculate the count rate, which will correspond to the activity of the source. So in the case of 100% detection efficiency, it will correspond exactly to the activity of the source, but we typically we don't measure all of the radiation emitted from a source. So we need to take into account also the detection efficiency. But if we do this measurement a number of times, so we measure the number of counts that we get from during a given time. So we have the same measurement time every time. And we repeat this measurement, we will get different results every time. And this is simply due to the stochastic nature of the radioactive decay, because it's not, your source will not emit a fixed number of gamma rays in a given time, but the probability, it has a fixed probability of emitting a gamma ray in a given time, but this can of course vary. So if you would do this measurement a number of times and then you would histogram the number of counts that you get, you would get a distribution looking something like this, where you have the number of counts on the x-axis and then the probability of getting that number of counts on the y-axis. So this distribution is a Poisson distribution with mean m and a variance given by sigma squared, standard deviation squared, which is equal to m as well. So this expression gives you the probability of achieving a certain number of counts n if you have a Poisson distribution with the mean m. So if this is the case, then how do we know what the true value of n is? How do we obtain that? So we can either perform the measurements multiple times, as we did here, and then we can determine the mean value, and that mean value would be the best estimate of the true value. So this is, however, quite impractical because it's very time consuming to do the measurements multiple times. So a second approach is to do just a single measurement and then associate an uncertainty with the value that you measure. And based on what we saw, the characteristics of the Poisson distribution, the uncertainty in the measured value n will be given by sigma equals square root of n. So this has a very important implication if we look at the relative uncertainty. So we see here that that's given by square root of n over n, which is 1 over square root of n. So this means that the relative uncertainty in the value that we measure will go down quite rapidly as that value increases. So this implies that we can increase the accuracy of our measurement if we increase the number of counts that we measure. So if we imagine a nuclear imaging system where we want to measure the activity of radiation located in a specific region in the body, there are three main ways which we can increase the accuracy with which we determine that activity. So we can either increase the measurement time, because if we measure for a longer time, we will measure a larger number of counts if the activity is the same. And we can also increase the activity, but keep the measurement time short, and because that will also give us a larger number of counts. However, it's quite evident that neither of these two options are very good, because we don't want to have a very long measurement time, because that's not very comfortable for the patient or very practical in terms of patient throughput, and there are many reasons that we want to keep the measurement times as short as possible. And we also don't really want to increase the activity. We want to keep the activity as low as we can because we want to limit the dose to the patient because of health concerns. So the third thing that we can do to increase accuracy is to increase the detection efficiency, which really highlights. So by detection efficiency, we mean the maximizing the fraction of those gammas that are emitted from the radio tracer, and we want to maximize the fraction of those gammas that we actually detect. So this highlights what we've been talking about before, that we need detectors with high stopping power so that we can detect as much of the radiation as possible. So this slide really shows us why this is important, because it will ultimately improve the accuracy of our measurement and impact how good of an imaging system we will have. And this condition that the standard deviation equals to the square root of n, this applies only when n is a measured number of counts. And often the final quantity that we are interested in is a function of one or several counting measurements. We can be interested in the count rate, for example, or something that's a function of the count rate. So then we need to propagate the uncertainty in each measurement to the final quantity. We can also typically we want to look at the differences in measured number of counts, because we want to see if an activity is higher than compared to another activity. And then we need these uncertainties. So if we assume that individual measurements are independent, the errors can propagate according to this formula, where this is the u is a function of x and y and z. Then the uncertainty in u is going to be a function of the uncertainty in x, and uncertainty in y, and uncertainty in this way. So if we look at some cases, if we have u is a sum or a difference between x and y, then the uncertainty will look like this. It would be the square root of the sum of the squares of the uncertainties. Or if we have multiplication or division by a constant, which we would have typically when we calculate the count rate from the number of counts, the uncertainty will propagate like this. And then we can also have multiplication or division, where we would get the relative uncertainties. The square of the relative uncertainties should be summed to get the square of the relative uncertainty of the final value. And this slide shows, because when you compare, when you want to compare different measurements, for example, see if what you measure is higher than background, for example, you need to compare those measurements based on the uncertainties in the measurements to see if they're statistically different. So this just shows the confidence level, how confident you can be in your measurements for, so for example here, if you have the number of counts that you measure plus minus 3 sigma, it's 99%, more than 99% probability that your true value is within this region around your measured value. So differences greater than 3 sigma are generally considered significant. And if you have a difference of less than 2 sigma, you will have at least a 5% chance, because the confidence level is 95%. So you will have at least 5% chance that the difference is caused by random variations, and it's not a real difference. And you typically talk about minimum detectable activity, which is the activity that increases the count rate by at least 3 sigma compared to background, which is when you can say that you are actually measuring something. It's not just a variation in your background. So that was all that I have for today. So if you have any questions, I'd be happy to answer. There seem to be no questions.
Yes, yeah, so it appears that we don't have any questions. So
no. Crystal clear.
Yep. If any questions do come up as you're mulling things over, feel free to email me or Lisa regarding whichever questions you have. And just as a reminder, please email me. I put my email in the chat. It's also on the course schedule to be added to the course Dropbox for slides and homeworks.
Yeah, and I'd be happy to answer any questions like over email individually, or if there's something you want me to talk about on Thursday, I'd also be happy to do that. So just reach out.